When we talk gases and we look at how we developed and determined the ideal gas law, the ideal gas law is based on the proportionalities and the empirical relationships discovered between all of the physical properties: volume, pressure, temperature, and amount of gas. And so these relationships, you explored them when you did the PhET simulation and looked at the graphs from either the notes or the ones that you created. In essence, when we see this proportionality, it allows us to put all of these together in kind of a single proportionality. So now we have this new proportionality where we've combined everything. Now, when you look at this, this simply tells us that amount of gas, temperature, and pressure are all related to impacting or have an impact upon the overall volume of a particular gas. Now, remember from the book, it talks about how when we look at this, really what we're looking at is we can put these together and we can say something like PV is actually equal to some constant. Well, if we incorporate the constant into this expression, then this is what leads us to the ideal gas equation. The ideal gas equation being the introduction of R, the ideal gas law constant. The main thing to remember about R is it is unit dependent. So depending upon the units that you are using, R has various values, and those values are shown in table 10.2 in your book. Notice common ones that we're used to seeing: liter, atmosphere, mole, Kelvin. Notice we can also incorporate joules, calories, meters cubed in pascals, liters torr, etc. These are the ones that you are probably most familiar with. These are a little bit different, but they have a use, especially when we talk about various things in thermochemistry or electrochemistry and things that we'll be using this equation for later on. Now, one of the great things about Pivner is our ability to use it for various purposes. So we can use it to figure out the density of gas. Remember that the density of a gas is, in essence, amount of gas over volume. So if we rearrange Pivner to show that, we can see that. However, we don't usually know the moles of a gas. We might know the mass of it. We might know its density. So we can rearrange this by introducing one more idea, and that would be molecular mass or molar mass. As soon as I incorporate molar mass, let's go back, whatever I do to one side, I do. So if I multiply by molar mass on this side, and I have to multiply by molar mass on the other side, and I see that moles times molar mass is going to give me just mass, because I know that molar mass by definition is mass per moles. So my mole cancels. And if my mole cancels, then I'm left with mass over volume, density, and I end up with pressure, molecular mass, my gas law constant, and temperature. So I can rewrite it. Mass divided by volume is density. So I have this equation, and you can use this to determine density of any gas under any conditions. If you know the gas, you're supplied with molecular mass, you can be supplied with pressure, you can be supplied with temperature. Again, R is dependent upon the units, so you always go back and just utilize the table. And the second thing is, the really cool thing about this is I can also then, if I know the density, I can solve for molar mass. So I can rearrange it, solving for my molar mass, and now I get, as Mr. Richardson says, I need to keep my dirt over my P. So you cover your P with dirt, and you can always solve for molecular mass. And all we've done is rearrange the ideal gas equation. So here's a sample calculation related to determining molar mass of a gas. And this is the sample exercise in 10.8. What I would like you to do is pause the video, solve the problem. After you've solved the problem, then go find the answer in your textbook. And 10.8 in your textbook, it literally lays out how to solve the problem, but I want you to solve it first utilizing our basic equation here. So pause the video, solve it, check your work. Any questions, bring up in class. The next application for the ideal gas law is in stoichiometry. The big thing to remember here is when we deal with stoichiometry, what we're dealing with is the gas as either a reactant or a product of a chemical equation, a chemical reaction. So for example, if we talk vinegar, I have NaHCO3. So I have vinegar reacting with baking soda, and I'm going to produce sodium acetate, water, and carbon dioxide. So in essence, I already know that carbon dioxide is my gas. I know I can look at this and determine the mass of the gas I produce. I can determine the moles of gas I produce if I know either one or both of my reactants. I can even do it if I know the amount of one of the products because it's stoic. The big difference here now is you can look at a gas and treat a gas the way we would in terms of volume, in terms of pressure. So what the ideal gas equation allows us to do is to take the moles, because I know that N equals PV over RT. So I can take the moles of my gas and I can determine, if I know the moles, I can determine pressure, volume, temperature, as long as I know any of the other two. Typically when we deal with stoichiometry, we will use the ideal gas equation either to start the problem or to end the problem. And this is because we know in stoic we want to get to moles, we want to utilize the molar ratio, and we want to get out of moles. So recognize the point that I'm going to use the ideal gas is going to be to either get moles, meaning I solve for N, or to get out of moles, in which case I'm either solving for pressure or solving for volume, because the stoic problem gave me my moles of gas. So you just have to recognize when to use it. So if I start with the gas, if I'm given the gas information, my gas is my given, then Pivnert's first and my stoic is second. Okay? Conversely, if I am solving for the gas, then I need to do stoic first so I can get to the moles. Okay? And I'll do Pivnert last because I'm probably solving for pressure or volume. So again, it's just practice using these basic ideas. And stoichiometry and gas laws are a review for you. You've already done all of these kinds of problems. Now it's just practicing and using them again. All right, so the next idea, Dalton's Law of partial pressures. Now, the reason this is considered an application of Pivnert really has to do with mole fractions. But quick practice with Dalton's laws of partial pressures. You already know that pressure 1, pressure 2, pressure 3 adds up to a total pressure, because if you add air to a tire, the pressure keeps going up. It doesn't change. This is because gases behave like they're islands unto themselves. So they react and behave like they're the only gas present. So, quick question. If pressure is exerted by nitrogen, is it affected when oxygen is added? Okay. So, if they behave as islands unto themselves, then will nitrogen be affected? Will any pressure, amount, volume, will that all be affected by the presence of oxygen? The answer is no. So that means nitrogen gas is not changed with the addition of oxygen. Okay? Now, that means if we're talking mole fractions, if I have gas A and gas B and I want to mix them, I'm going to see a change related to them. Now, mole fractions, since they're based on this, remember that P1 equals N1 times RT over V. Now, the reason that we put RT over V in parentheses is because if they're in the same container, they're going to have the same temperature. If they're in the same container, they're going to have the same volume. So that means that my pressures are really a result of my moles, the amount of gas I have. So let's rearrange and solve for N. That means N equals PV over RT. Now, again, whenever I look at this, if I'm talking mole fraction, remember this is our giant X, mole fraction is really the part over the whole. So N1 over NT. So just like a partial pressure is based on a percentage, a fraction or ratio, so is mole fraction. Except now, I take this whole thing. Now, what's cool is, again, since RT and V were the same, guess what? RT are the same when I mix them. If they're the same when I mix them, I can just ignore that. So literally, my mole fraction can be my part, pressure volume, over all of the pressure volumes of the component gases. Now, remember, which is similar to the notes that we've already done, if my pressure is the same, hold on, let me get a pen. At the same pressure, my mole fraction is literally a volume fraction. Volume of my part over volume of the whole. Because if my pressure is the same, it has no impact on the overall calculation. So it's literally the volume of the component over the total volume when you mix them. When the pressure becomes important is if I have the two separate gases in the apparatus at different pressures. Then you have to account for the pressure because that's going to change your mole fraction. So I'd like you to pause the video, solve for the mole fraction based on this information. If when I turn the stopcock and I allow the gases to mix, what is going to be the mole fraction of your hydrogen gas? So when you set this up, you should have put the part over the whole. So here's my H2 over my H2 plus O2, part over the whole. When you solve, you should get 9 plus 10, so 9 over 19. So my mole fraction for hydrogen is 0.47. Now, where this becomes important is when I collect a gas over water. That means that my dry gas is going to have a different pressure from the mixture of dry gas and water gas. Again, the importance here is anytime I collect over water, I have water vapor. And the interesting thing about the water vapor is the water vapor pressure is temperature dependent. So you know the temperature of your water, you know the total pressure of your contributed by your water. Because this total pressure here, as long as my water level inside this container is equal to the water level on the outside, that means the pressure inside is equal to the atmospheric pressure. My total pressure is therefore a result of whatever gas I collected and water vapor. So it's a partial pressure issue. So I know in partial pressure, P1 and P2 is going to give this to me. That means to know the pressure of my gas, I simply take my atmospheric pressure minus my water pressure, my water vapor pressure, to get the pressure of my dry gas. And that's it. It's just an application of your partial pressure.